Autobots wage their battle to destroy the evil forces of the Decepticons, the Transformers. Robots in disguise. The Transformers. More than meets the eye. The Transformers.
Welcome back to the Lowdown on Physics. That was just too good an intro to actually talk over. This is screencast number 8 in a series on electric power in Unit 4 VCE Physics. Today we'll actually, surprise surprise, be looking at transformers. So if we're not talking about transformers of the Autobot kind, what exactly are we talking about? Effectively, when we generate a voltage and current, usually it's not of the magnitude that we require, so it's either going to be too large or too small. So what transformers do is that they change the size of the voltage. Now, since power loss is proportional to current squared, because P equals I squared R, and P equals V times I, it's more efficient if we send it at a high voltage, low current. But we'll talk more about that a little bit later on. So that's what a transformer does. What exactly is a transformer? Basically, it's a very simple device that can change AC voltage from a low voltage to a high voltage without changing its frequency. Or, obviously the other way around as well, high voltage back down to low voltage. What this also does is result in a change of current. Since the power will remain the same, if you increase voltage, current must decrease. Or if voltage decreases, current must increase for the power to remain the same. Now, basically what is it? It's two coils of insulated wire, and they're wound around a soft iron core. Again, this is all about creating a magnetic field, the magnetic field inducing a current and a voltage inside the secondary coil. So similar to when we were looking at motors and generators, we have the soft iron core there because it's going to increase the strength of the magnetic field, but the soft iron core won't stay magnetized. What it does is then responds really quickly to the changes in magnetic fields, and that's due to the changes in the current. And effectively, it's really going to direct that magnetic field from the primary coil, where we've got our initial voltage, into the secondary coil, where we want to change the voltage and current. So in its simplest form, we would have our AC power supply. It comes in, it's in a coil of N P turns. The P is for the primary, that's our input coil. And that's going to produce a magnetic field. So basically a coil, or like a solenoid as such, is going to produce that magnetic field. We've got the laminated core, so that's going to help drive that magnetic field through the secondary coils. So we've got N subscript S for the secondary. This is our output terminal. So some voltage here produces a magnetic field. It induces a current and voltage here as our secondary output. So most importantly, we need a different number of turns between the two coils. If we have the same number, we're effectively going to produce the same voltage as we started with. So we want more turns to produce a larger EMF, or we want less turns to produce a smaller EMF. So how do they work? Let's have a bit more of an in-depth look at it. So you've got electromagnetic induction, changing flux. This is why it's important that it is AC, because the flux will be continually reversing its direction and therefore continually producing an AC output. The changing magnetic field intensity as it goes through the second coil. This is what we've been looking at with Lenz's law and who was that other one? Oh, mind blank. You know who I mean. Correct me. Tell me. Can't hear you. Yeah? Alright, good. Okay, so that law, Faraday, thank you. Finally heard somebody speak up. Faraday's law. So looking at the changing magnetic field and where it, as it cuts the coil lines, it's going to induce that current. So the result that we get is that secondary, or that induced current, that induced voltage in the secondary coil. So to consider it mathematically, it's all done in ratios. This is really quite a simple technique once you master it, and it shouldn't take us too long to master. So basically the transformer formula is we've got Vs over Vp equals Ns over Np. So the ratio of voltages is directly proportional to the ratio of the number of turns. However, it is inversely proportional to the current that is produced in the primary and secondary coils. Now I'll show you just in a second why that is. Key thing is, if the secondary voltage is greater than the primary voltage, it's called a step-up transformer. If the other way around, we produce a smaller voltage, then it's called a step-down transformer. In an ideal transformer, energy is conserved. So power in equals power out, or VPIP equals VSIS. If we look at this equation, if we divide by IP, we divide by VS, we end up with VP over VS equals IS over IP. So we get that inverse relationship from this equation. If you want to see that on the board, then I suggest me to show it to you in class, then I suggest you whack something on the forum so that I can explain it. Otherwise I am led to believe that there's no questions and you understand all of this perfectly.
The Transformers! Robots in the sky!
So why the laminated core? I mentioned something in class about this the other day, and it's totally to do with ensuring that we minimize the amount of loss of flux that's passing through. It avoids or reduces eddy currents forming in there, and that's really all you need to know. Okay, let's have a look at this example. So let's consider what's happening here. Current in the primary coil is 0, so we have 0 current in the secondary coil. As the current increases, we produce a current in the secondary coil. It's a constant rate of increase. That means that we get a constant current in our output. Okay, so why is that? Because this will change the amount of flux that's passing through the secondary coil. There's going to be a constant increase in the amount of magnetic flux, so we get a constant induction. The next point, there's no change. It's constant current. Constant current means no change in flux, so we get no output in the secondary coil. We now get a decrease in the current. There's a constant decrease, so we get a constant change in magnetic field, and therefore we get a constant current output. Notice here that the gradient is less, so the actual magnitude is going to be smaller. Then we get this last point here where we have constant or 0 current and 0 current output again. Okay, so let's have a look at an example with some numerical values. So we have a transformer. It has 2000 turns in the primary coil. That's the one that we input into. And it has 5 different options that you could plug into for your output. So your secondary coil, you could connect to 100 turns, 200 turns, 300, 400 or 500 turns. Now, primary input or primary voltage is 240 volts. What should you connect to on your output for 12 volts to run a 12 volt soldering iron? So if we use our equation, we've got Vs over Vp equals Ns over Np, already substituted into, should have written the formula first. Rearranging, we're going to multiply both sides by 2000. So 2000 times 12 divided by 240, we get 100 turns. So the output would be 12 volts if we connect to the 100 turns. Out of interest, what would the output be if we connect to 200? It's going to be double the number of turns. You're going to get 24 volts, 36 volts, 48 volts, or 60 volts from the 500 turns. Okay, second example. What ratio of turns is required if we want to go from 240 volts to 6 volts? So this is a ratio, not a given value. So basically, if we're talking ratios, we're just going to say 240 to 6, or simplifying down, we'll divide both sides by 6, and we get a ratio of 40 to 1. So for every turn in the secondary, we need 40 more turns in the primary. Now, the secondary coil has 50 turns. How many do we need in the primary? So again, here we've got 40 to 1. So if this is multiplied by 50, this side also needs to be multiplied by 50. So 40 times 50 is 2000 turns. If we run 240 volts through the primary coil, what is this secondary voltage? Okay, you can probably figure that out going on the first example, 50 turns, but let's substitute in anyway. Vs over 240 equals 50 over 2000. 240 divided by 50, multiplied by 50 divided by 2000, we get 6 volts as our secondary voltage, or our output voltage. So next one, we'll actually look at how to apply this to transmission of power and power losses in power lines. And then we are done for this topic.
The Transformers, robots in disguise. The Transformers.